So we have this function, this graph of this function in blue. One thing that maybe wasn't 100% clear, but was meant to be there, is that this bottom line that is in bold is supposed to be the x-axis. And that is relevant because we care about the area between f, the blue line, and the x-axis. So the triangle we're talking about is this triangle over here. I think probably most people figured that out. You have to use the formula 1/2 base times height. In this problem, the base is 4. The base is 4. You could also do 2 triangles with base 2 each. That would also be fine if you want. But I think it's easier to say the base is 4. And so if we use the formula 1/2 base times height, we get 1/2 times 4 times the height has to be equal to 1. And if you solve, you get, drum roll, what do you get? You get an answer of 0.5. Very good. So almost everybody, 47 people answered, 37 people got 0.5. If you got 2, you probably made like a 1/over error, little algebra error. If you got -2, this is an important thing, is that all of our functions are always going to be above the x-axis. And we'll see why that has to be in a second. So we're kind of dealing with functions that are always above, and we're always dealing with positive areas. The height, the f of 0, has to be positive 0.5. That is the correct answer. Okay, so once again, let me write down a summary of this thing. This is a little warm-up problem. Is going to help us when doing these little calculations. And so we're doing a warm-up. What height makes the area equal to 1? And once again, the reason we want the area to equal 1, we'll see that this 1 is the 100%. We'll see this is the 100% from before. So just like we always want our probabilities, our random variables have to have a 100% chance of being somewhere, our areas always have to be equal to 1 for the total area. And in this particular problem, we had something going from x equals -2 to x equals +2. And we called the function f of x. Let me give the x-axis a different color. This down here was the x-axis. This is the x-axis. And we said, please find the value of f of 0. That is the height at the origin, when x equals 0. And in this situation, the height at f of 0 is the height of the entire triangle. So we can use 1/2 base times height. Area equals 1/2 base times height. And then you plug in what you know. 1 equals 1/2 times 4 times h. Therefore, the height has to be 0.5. And that was the warm-up problem. Okay, very nice. So why do we care about this? We're going to move in to calculating probabilities using areas. And this is a new type of random variable called a continuous random variable. And we also have some nice slides over here, but I'll give you my little chalkboard definition. A continuous random variable, and let me be very practical about it, and say how you calculate with it, has probabilities which are calculated by areas under a function f. And by under, I mean exactly this thing between f and the x-axis. Okay, and here are some bullet point things. This is is this a definition? Maybe this is not a definition. Maybe this is a idea. We'll have the exact definition in a little bit. Idea. But here are some things you should know. This function f is called the probability density function. Okay. It's important you don't mix up a probability density function with a probability mass function that we saw before, and you don't think that f gives the probability directly. So the same way the height of this triangle is 0.5, that doesn't tell you about the area, right? If you have an area, the area will not be the height. Of course, the height will factor in somehow into the area, base times height, but the height on its own does not tell you the area. The area is the thing that is the probability. So let me highlight the word area over here. Areas, those are important. So the area, probabilities are areas. Okay. F is called the probability density function. Here are some facts about F. Must be positive. Must be positive. You can't have any negative numbers. I guess, okay, say let's positive or 0. It can be equal to 0. That would mean there's probability 0 chance of something happening. We've seen that a lot. F has to be positive or 0, and the total area of F must be exactly 1, just like we saw before. So a good example is the example we just did. Example, let F be the triangle from before. So here's the triangle from before. It goes from x equals -2 to x equal +2. Here is x equals 0. And here is the triangle. And we calculated the correct value that f of 0 has to be equal to 1/2. And that makes f a proper probability density function. And now let's do some calculations. Here is the rule. The rule to calculate probabilities. Okay, so I'm gonna write it like this. Highlight the part of the x-axis you are interested in. So as an example, if someone says, please find the probability, let's say that x is between 1 and 2, 1 less than x less than 2, you would highlight the region on the x-axis that goes between 1 and 2. So you take x equals 1 to x equals 2, and you would highlight like this. So it's this area, this little region on the x-axis is what I care about. And you can kind of think about this as a piece of the x-axis. And this is the key thing. So when someone talks about values of the random variable, like I want the random variable x to be between 1 and 2, they are talking about a chunk of the x-axis. So this is why it is nice if your random variable is called x, then everybody is happy. X is over here, x is over here, everyone's happy. Of course, be careful because some random variables are called y, but they still go on the x-axis no matter what. So this is the first step. And then the second step is the probability is equal to the area under the graph here. The probability is equal to the area under the graph here. Okay, and let's make this orange. So the area, if you want to know the probability is always going to be some kind of area, and in this case, it's the area that corresponds to this chunk of the x-axis. In this case, it's the area of this little teeny tiny triangle. That triangle over here. And so you have to be able to do some basic geometry like an elementary school student and know, hey, this is a triangle that has base 4, it has height 1/2, we calculated that already. What is the area of that little triangle over there from x equals 1 to x equals 2? And there are a lot of different ways you could do it. One fancy way is to use something called calculus. You do not need to use calculus in this course. All of the pictures will be little triangles and things like that, where any fourth grader who studied their triangles will be able to figure it out. In this particular case, I would do it by similar triangles. I would figure out something using similar triangles. But let's give you guys a minute to try to figure it out. So see, can you figure out what is the probability x is between 1 and 2? It's the area under this little triangle. Okay, I will give you guys a minute to do it, and I'll put it up on mathmatize, and I will have you attempt it. Any questions or comments before I set you loose? Okay, let's attempt it. This is a problem. Okay, it is up on mathmatize, but I will show the board because that has more helpful information, and then you guys will try it and tell me in say a minute and 30 seconds to give it a go. Let's take a look at what people said. I have to open this up. Yeah, almost everybody has answered. And yeah, so for some people, I think this will be very, very easy. And for other people, maybe you have to review a little bit how these area calculations go. But it's not some fancy new theory. It's area. OK, what did people say? OK, 1, 2, 6. Remember, 1 is the total probability. So unless x equals 1 and x equals 2 are the far ends of the whole thing, it can't be 1. It's always going to be less than 1. So 1, 2, and 6 are not great guesses. But 1/8 is a very valid thing. If you put in 3/2, you might have had a flip. Maybe you meant 2/3. So things like a quarter, very nice. Square roots do occasionally come into play, but in this case, I think the answer is indeed 1/8. So just under half the people got it. So maybe I will do it a little bit more slowly to show you how it is done. There are a few different ways you can do it. So the answer is indeed 1/8. Here is how I would do it. The bread and butter way is I would say let's calculate the height of this thing. That is what I need to calculate. And I would do it by using proportionality. So I'd say this little orange triangle that I want is proportional to the big triangle over here. The big triangle has a height of 1/2 and a base of 2. So the big triangle, the height equals 1/2 and the base equals 2. And so if I look at this little red triangle, this little orange triangle over here, the small triangle, I would say the height equals question mark, but the base equals 1. And because they are similar, they have to be in proportion to each other. So I can see that the small triangle is actually half the size of the big triangle. You could also do it with ratios. So you could say 1/2 over 2 equals h, the h I'm looking for, divided by 1. And then you could solve. However you want to do it, you should get the final answer that the height equals 1/4. 1/4 is the height over here. And then you use 1/2 base times height again. So equals 1/2 base times height. Don't forget the 1/2 like I always do. You get 1/2 times 1 times 1/4 equals 1/8. I think that is the most straightforward way to do this one. In this particular problem, you could also, there is one nice clever solution, which is you could start drawing all sorts of little triangles on your shape. Remember, we just want to find the area of the little triangle. We know the total triangle is area 1. And I claim if you cut it up like this into sort of a Zelda Triforce kind of thing, there's 8 of these triangles, and they're all equal in area to this. So this is one piece. There's 1, 2, 3, 4, 5, 6, 7, 8 equal pieces. So each piece has to have size 1/8. That is kind of a clever way to do it. That won't always work. So maybe it's better to know the sort of straightforward way. Any questions or comments about how I calculated the area? OK.
Professor Nika.
Yes, please.
I have an interjection.
Yes.
So on the mathmatize there, correct answer was 1 out of 8. but there were some answers in there that our automatic bullshit detector should detect. And we are calculating a probability, and what do you know about a probability? It can't be less than 0, and it can't be greater than 1. So if you make a mathematical error or calculator error, etc., which happens all the time, and you end up getting a probability of 2, what do you know? You know you have made a mistake, right? That is the only way you are going to get a probability of 2 is you have made a mistake. There are no exceptions to this, to the probability falling between 0 and 1 inclusive. So again, if you come up with those numbers, say to yourself, oops, I have screwed up somewhere. And then look for where you screwed up, okay? Or if you ever get on a test where you screwed up like this, and you just can't find the mistake, which happens sometimes, you just can't figure out where the heck you've gone wrong. You've got this number which is impossible. State, clearly impossible, but I don't know where I went wrong, okay? That's worth more than just leaving it as a probability of 2 or something like that, a probability of -1, right? Does that seem fair? Seem fair?
Yes.
Seems fair.
Yeah. I mean, if you write something like the probability is 2, then the person grading it says this person has no idea how probabilities work. But if you write this makes no sense, then the person goes, well, at least they know that it makes no sense. So you want to, when you, like, you know, humans are grading your tests, and the humans are trying to figure out how much probability you know or don't know. So keeping that in mind can be helpful. Okay. Really, what we have shown you is the core technique. This is if you understand this rule and you understand the basics of areas, and you know this idea of the probability density function, you can answer all the questions that are on that the work problems for the midterm. I will say, you know, there's like more kinds of things you can do. They're all extensions of this idea. A good here's an example of another sort of quick one. We could say something like, is x more likely to be near 0? To be near 0, or more likely to be near 2? And I'll say let's to make this concrete. Let's say let's compare the probability that x is between -1/2 and 1/2 versus the probability we just did. The probability 1 is less than x is less than 2. Those are two numbers. And one way, of course, to do this is to calculate it. But again, if you know this idea of what we are comparing is actually areas, then it becomes a picture kind of proof where you're comparing two areas. And the area for between 1 and 2 is something we've already done. Right? This is the orange area that we've done over here. And we have this kind of new area let me highlight this in yellow. So between -1/2 and 1/2, that is the region over here near the peak of the triangle. And so if you know the rule, oh, you should look on the x-axis between -1/2 and 1/2. You have this region of width 1/2 comparing to this other region of width 1/2. Which one has larger area? You could calculate them both and figure it out. That would take a little bit longer, but you can tell just by looking that the yellow area is bigger because it's taller. So they have the same width, but the yellow one is overall taller than the orange one. And so this is a larger probability. So this is the kind of question, this is larger, that you can answer. This is larger because it has more area. And the reason it has more area is because the density function is larger. So once you kind of get the hang of this and start doing more and more complicated problems, you can sort of get more and more intuitive feels and figure out all sorts of interesting things. But for now, this is the only thing that you absolutely must know is how to do this. Okay, we have a couple other little true-falsy type questions for you, but we also have some sort of applications here, some slides about that. So maybe we'll do that first, unless there's any questions. Okay, let's do the slides here about different applications.
Just a couple slides, just to get the definitions down smooth. And let me Get this, okay, let's just get this from current slide. Got that. Got that. And is it showing up? Oh, my goodness, it's doing it just right. Okay.
Very spooky.
Okay. So, key thing is everything we've been working up prior to today has been discrete random variables. So let's just check our definitions of discrete random variables. Discrete variables take on either a finite number of values or a continuously infinite number of values.
Wait, hold on. You said continuously infinite?
What did I say? Continuously infinite?
That's the opposite of what we want.
Where? They take on a finite or countably infinite.
Yes.
Oh, did I say continuously?
You said
oh, how embarrassing.
Well, I think the main thing is we've seen this word, we don't know what it means yet. There will be a future lecture where we will tell you what countably infinite means. For now, you just have the vibes, okay? It's like, 1 or 2 or 3 or 4, like if you can start putting them in a list, in a nice big list, even if that
we did
list
see
is
it with
infinite.
geometric random variables,
Yes,
right?
yeah, that's
That
an
was
example.
countably infinite.
Yes, but this is like defining, I haven't told you what a horse is. I just told you this one is a horse.
This one is a horse, yes.
Yeah, right.
Okay.
So they don't know what countably infinite means yet, and that's okay. We'll learn later. But finite for sure. Anything you can put in a list, that's a discrete.
Right. Okay. So our continuous variables can, at least theoretically, take on any value on the real line over some interval. Okay? And you probably are going to have a lot more to say about that. Yes, I think so.
Yes. Well, so a good example is the one we just did with the triangle. That could be anything from -2 to 2. That's where the density function was positive. So anything between -2 and 2 was a valid thing that it could happen. Could be like -1.5673214, decimals going on forever. That could happen. So that's the difference between continuous and discrete. Is really you can have sort of infinitely many decimals, and that ruins this finite thing. There's infinitely many values it can take on because of the infinitely many decimals.
I cannot get an infinite number of decimal places on my calculator.
Yes, that's a different story. Yeah,
That's a different story.
Yes, it will. It will be true that the probability of being any individual value will be 0. If we go back, this is a very good thing to notice, right? We said the rule is you highlight the area you care about on the x-axis, and then you find the area. If the thing you care about is one single point, you say, what is the probability that x is exactly equal to 0? What is the probability? If someone says, please find the probability that x is exactly equal to 0, then you would highlight just this little one dot at x equals 0, and what is the area of that vertical line? It's 0 because its width is 0. So this is an important thing to realize. There's infinitely many values, and every individual value is 0, but somehow they can combine together to give non-zero things. Sounds very spooky, but then you realize this is the same thing as the way areas work, right? You have infinitely many lines. Each line has area 0, but altogether they have some total area. It's exactly the same phenomenon because we're doing it with areas. So yeah, that's a great point. Okay. Yes, this is why the infinity is a little bit subtle. You have to be a little careful and not say the wrong thing about infinity.
So, of course, we don't typically measure anything to an infinite number of decimal points because we get really two things, limitations on our measuring equipment as to how precisely they can measure things. That can be one reason. The other thing is there any real information in those extra decimal places? So if we measure somebody's height, maybe there's a certain precision to how closely we can measure their height, but there's also a point, is there any real point of knowing their height to 56 decimal places? Probably not, right?
The way I like to think about this one is, even though to me, this is a little bit of a philosophy thing. You could say continuous random variables don't exist because you can only ever measure to finite precision. But the way I think about it is continuous random variables do exist. They are some real thing in the universe. But the questions you are allowed to ask, you are not allowed to ask a question like, is x exactly equal to 0? You can only ask questions of the form, is x in some interval? Maybe you say x is less than 0.0001 and greater than -0.0001. So if your precision is only 4 decimal places, then you can only resolve questions of this form. And so you can never see the true nature, right? You can only have a certain level of precision. But nevertheless, to me, the random variables really exist like this, and your precision comes into what kinds of questions you can tell the difference between. Other people will have different takes on it. I'm not sure. What do you think, Gary? Do
No,
continuous random variables exist?
They exist in both a theoretical way and kind of in a real way too.
So they certainly exist as a theoretical thing. Do they exist in the real world? You can either say, because of this precision thing, that they exist and we can only measure with so much precision, or you can say every time I'm doing something, I'm actually doing a discrete random variable that is just very closely approximated by a continuous random variable. But yeah, we're going to use them. They're very useful. They're super useful. Yeah, question? That's right. Yeah, this is what you have noticed is that when someone tells you a function, right? When I say draw this triangle function, I've actually specified an infinite list of y values, right? So if I want to tell you all the y values on my thing, I could describe it as a line and a line. That's very simple. But I could say at x equals -2, it's 0. At x equals -1.9996, it's 0.0001. So there are an infinite number of things that are in this thing. They're all baked into this one picture. And so it is an infinite amount of things, but don't be scared of it. It's just a function that contains all the information.
So this one here, you could calculate a probability. It'd be very, very small, but let's add some extra zeros in here. And instead of 0.0001, we make it 0.000001 on both sides. And that probability gets smaller and smaller, and you can just think of adding more and more zeros there, what that's doing to the probability. And how many zeros would you recommend
Well, this
adding?
is for the people in calculus class. They have the nightmare of seeing epsilon delta in 2 of their classes. So you can make
enjoy that though, right?
You can make the probability as close to 0 as you want, as long as you add on enough zeros here. And so we don't pre-specify you need 4 zeros or something. We let it be loosey-goosey, and depending on what you want, you can specify more or less zeros. All of these issues are quite subtle, and they're not a core part of this course. If you can use the rule to calculate the probabilities, you're going to run into this kind of issue in your later probability courses in 3rd and 4th year. Yes. Okay. Great question, though. Any other questions about the nature of reality? No. Okay. Well, let's stick to our regularly scheduled programming. Okay. Yeah.
Our regular scheduling program.
Okay.
So
Why
just
are they
some
so useful?
examples.
Why do we torture ourselves with these? Oh, look, there's a nice list. Okay.
So examples of some continuous random variables when we measure things at time, length, area, volume, weight, temperature variables those are some of the simple continuous random variables. And yes, we do measure them to a certain level of precision, but there's nothing that says, at least theoretically, we couldn't measure them to even further and further decimal places. Okay, so these are, of course, very common variables that we measure and need to do some sort of analysis. Okay, so a second slide here is to distinguish between the probability mass function for a discrete random variable and the probability density function for a continuous random variable. So let's just note that the probability mass function for a discrete random variable assigns probabilities for each possible value of the random variable. Technically, it assigns it to any value in the sense that we say, well, we often use this 0 otherwise thing that, we roll a die and it can come out 1, 2, 3, 4, 5, or 6, and we say, well, what's the probability we got a 7? And we say, well, that's 0. What's the probability it was 11.32? That's a 0. Okay, but it's assigning probabilities to each value each value of x. And the ones that we typically are most concerned with are the ones for which it assigns probabilities, non-zero probabilities for some values of x. And so key takeaway from this class, a key takeaway, which Professor Nika has been stressing, is that the probability distribution for a continuous random variable, it does not assign probabilities to each possible value of the random variable, and instead it assigns, or it is used to assign a probability that the random variable will fall within an interval of possible values. And we call that a probability density function. So really the key thing is to recognize that the values of the probability density function do not assign probabilities directly. All they do is give you the height of the curve at a particular value of x. And we will see that the value of a probability, the f of x, the value of the probability density function, it is not constrained within 0 and 1. Well, we'll look at what are the constraints. Does it have constraints? Well, it has
we'll say
some constraints.
If you've taken physics class and you know these words mass and density, the words are actually quite suitable here. So if you imagine if I had a bar of steel in front of me and I said the density of this bar of steel is 1 kilogram per meter, well, how much does one little chunk of it weigh? It doesn't weigh a whole kilogram. To get the weight, you have to multiply the density times the length of the bar. And it's the same thing with the probability density function. The probability density function doesn't directly tell you the probability. It tells you the height of which, if you do base times height, you will get the probability. So it's a little bit like density. I will also say, when we were doing R many weeks ago, and we kept getting screwed up by D binom, we were like, D binom. Why is it D? Well, this is why it's D. D stands for density, even though in R that was a probability mass function. But I guess they call all of the ones D, even if they're
bad choice.
Yes, but that's what the D stands for density.
Yeah.
Okay.
Okay. So, do we want to do this example, or do you want to go to a different example? Let me just take a look. Let me just take a look. I'll just let me just freeze something for a second here. Let's just say here.
I think the freezing only works on 1 out of 2.
Oh, it only works on 1 of the 2. Okay. Well, just give us a second. We're just contemplating. Do we want to do that one? So I like time intervals, but you may have another thought on this.
Yeah, why don't you do the time intervals, and then we'll do this problem right at the end. We'll do this. This mathematize will take 5 minutes.
Okay.
Okay.
Okay, so we worked with triangles. Even simpler is to work with rectangles. And one of the, a simple example to think about is something called, well, we'll give it a name. We'll give it now. We'll do it more formally later on. Something called a continuous uniform interval. And consider something like your doorbell is going to, oops, oh, I know what I forgot to do. I forgot to get my pens out of my bag. My pens. Just forget something. Did I get that up? That question up?
Yeah, that was
okay.
Up a second ago. Okay, here. Now you have both.
Okay. Okay, just a sec. What if my light's wrong? That's what's messing me up. And then this thing is lined up wrong. Okay. We will eventually get this. Sorry, people. Why is my thing not where I want it? Okay. So a light will flash within a 100-minute interval, and at any time in the interval, any time in that interval, and if we take subintervals of any length, within that interval, the probability of flashing will be equal for any subinterval of that length. Now, why am I going through such a long way of putting this? Well, probably because I'm too wordy. Okay, so let's consider what does the density function look like? Okay, so I'm going to draw it this way, and I'm saying I've got this interval of 100 minutes, and what I'm saying is that this is our x-axis here, and this is f of x here, and no matter what interval I take, for instance, if I take an interval of 10 minutes anywhere in that interval, it doesn't matter where I take the 10-minute interval, the probabilities will be equal. Okay, or if I take a 1-minute interval, all the probabilities will be equal. If I take a little tiny fraction of a minute, let's suppose I take 1 second. 1 second, it doesn't matter where I take that 1 second interval, all the probabilities will be equal. And so what we've actually done here, this is an example of a continuous uniform distribution. Well, the random variable is continuous uniform random variable, and what we've done there is drawn the distribution for that random variable, so we'll call that continuous uniform distribution. And, it's continuous and it's uniform. Okay, so our first question is, what is f of x? So we were doing triangles before. Those were a half a base times the height. I think the rectangles are even easier.
Yeah, the rectangle, you split it into 2 triangles, and then you can use the 1/2 base times height formula twice. So if you know triangles, you know everything.
Okay.
Yeah.
So half times the base times the height, and multiply that by 2. I end up with just the base times the height.
Okay.
Okay, base times height. Okay, so if that's 100, this value's got to be 1 over 100. Okay. And we could write that out with a little mathematical equation. Okay, so if I said, well, let me just try this one. If we asked you what was the probability that the light would flash between 17 and 24, you would say, I need the height there. or not the height, I need the area between 17 and 24. And so the probability that x falls between 17 and 24, you would just work out what is that chunk of the area under the curve. And that seems pretty good. Give me an answer. 700s. Everybody get 700s? 700s, right? 7 over 100 now. We won't go over how to get that. Everybody get 700s? Anybody foggy as to why that was 7 out of 100? Okay, so that was between 7 and 24, but we're talking about this light flashing, and light's very, very fast, and we could talk about it in the sense that it's going to rise instantaneously sometime in that interval, and so we could keep shrinking our intervals smaller and smaller and smaller, and we could say, what is the probability that the light flashes within any 1 second interval? We could ask, what is the probability it flashes within any 0.001 second interval, or even 1 nanosecond interval, or a picosecond interval, or what's smaller than a pico? I don't know, but you know what I'm saying. We could do like picos of picos, something like that, right? So we can imagine that as that interval gets smaller and smaller, the probability is going to get smaller and smaller. It's going to get closer and closer to 0. Okay, so there's a uniform, and let's just go with...
We have a good mathmatize question we could do here.
You got a mathmatize question?
Yeah, it's actually
let's
kind of
go.
related to the thing you were just talking about. Amazing.
Okay.
Okay, it's a very, very nice one because it's a true-false. So true-false, and I have to press this button or nobody can see the question. True or false, it's possible for the probability density function to take on a value which is greater than 1. True or false? Let's just give you 30 seconds. If you are paying attention, we did mention this. And it is related to this idea of really tiny intervals. Really tiny intervals. What could it have to do with really tiny intervals? Take your best guess. All right, 10 seconds left. If you have no idea, just take a guess. Okay, let's see what people said.